Is there a question about any of the problems? Any? Nothing? All right. Well, I'm gonna pick one. I think I gave you the first 5, right? So I'm gonna show you how easy this is. And I'm gonna try and make it as clear as I can. Well, you really is a terrible simple. I'm going to start with 5, 6. But really what I'm trying to do is show you the basis for doing this and how easy it is. Now, I need your attention here because this is something, if you follow what I say, it'll be easy. But if you don't, and you try to learn this on the fly Thursday night, you're probably going to hurt yourself in a big way. So here, I'm just going to do 5, 6. And I'll mention everything. Here they have a voltage, and they say this source voltage, V of t, right here, is equal to 12 cosine of, here it's 377t, and then it's minus 60 degrees. I do not like this because that's degrees. 377 is actually radians per second. This is something I despise. It should be 60 degrees translated to radians, or pi over 3. You all follow me? Yes, sir. This is 12. Let me get a darker marker. I'm sorry about this. I'm going to try to put this in this dark marker. So they have V of t is equal to 12, and it's cosine of 377t, and then it's minus 60 degrees. Is that correct, first of all? I don't have my, anybody can confirm or deny that? There's something 60 degrees. It should be radians. You with me, class? Now, that's voltage. And then he says, in a way you can get away with it for this stuff. That's the voltage here, right here. V of t is right here. Then he only has one element here. And that element is a simple capacitor. Well, I think it's a capacitor, 500 microfarad. The microfarad is 10 to the minus 6 farads. Now, I'm going to ask you to please be extremely attentive here. The way we do this problem is go into the phasor or frequency domain. Do you all follow me? All right, what that means is this. Instead of putting 12 cosine of anything, we're going to put 12 as the magnitude, and the only thing we're going to worry about is the angle. Trust me on this one. All the other e to the j omega t terms will cancel with the differential equations that you write. Do you remember mentioning this on Friday? How many do? If you don't, just be attentive. I'm trying to get to the bottom line here. So I guess before I do that, I should say this. This coefficient of t is omega, or omega is equal to 377. Can everybody see that? Now the units of omega, if it's multiplying t, are radians per second. You can see if I have, is that plus or minus 60? Can you tell me?
Minus.
All right, minus. 60 degrees shouldn't be there. It should be pi over 3 radians. He gets away with it because of the way we're going to do the problem. So I just want you to be attentive. That, in fact, he's going to get away with, but you'll see why. Now that's omega, and omega is equal to 2 pi f. Do you all agree with that, class? If you do the math on this one, the frequency is 60 hertz. This is actually an example of a possible voltage that could be developed from that wall, because it is at 60 hertz or 60 cycles per second. Follow me on this one. Everybody? Now, once I have that, omega, I want you to understand this and write this down. If you have a capacitor, and there's a current I of t in the time domain, developing the voltage V of t across that. The relationship between V and I for this capacitor is simply C times dV dt is equal to I of t. You remember this? Right? This is basic physics. You had it. We mentioned this with the transient problems. When you go to the frequency domain, everything is varying as e to the j omega t. Do you all hear me on this? Now, because of that, when we go to the frequency domain, we're going to solve this whole problem in the frequency domain. What we find is that V of t, right, or I of t better yet, I of t becomes I phasor. Now, everything, and I'll get to the point here, is going to be changing as e to the j omega t. Or the omega is 377. Just go with me on this one. So I is equal to C times dV dt. A time derivative automatically brings out a j omega because the V of t is assumed to vary as e to the j omega t. This is a linear system. Just accept it for now. So that means it's j omega c times V phasor, or what we call the impedance Z, the ratio of V phasor over I phasor, when you're talking about a capacitor, is simply 1 over j omega c. Can everybody follow me on this? Now, j is a complex number. How many have had well, you're used to I. How many have had imaginary numbers? Everybody in here is supposed to be exposed to it in your math courses. However, j is the same thing as I in math. You all follow me, class? And what is 1 over j? Some people will probably remember this. When I talk about j, the first thing that they say, by definition, is the square root of -1, isn't it? Technically, it's plus or minus the square root, but don't worry about it. Just leave it as square root of -1. Now, what is that really? Well, j, if you think about the complex plane, if this is the real axis, and this is the imaginary axis, when I talk about j, I have a magnitude of 1 at an angle with respect to the real axis of 90 degrees. Has anybody else seen this illustration? Anybody? In math? They usually do this in mathematics. You've seen it? I frankly, sometimes I'm not sure what you've been exposed to, but all these things will be easy. So really what it's saying is this has a magnitude of 1, and it's at an angle of 90 degrees, and it's straight up. That's what it is. This is the real axis, that's the complex axis. Now, when I think about this, if I have 1 over j, what I'm really talking about is 1 over 1 e to the, and this would be j, and I'm going to go ahead and call it 90 degrees, even though it should be in radians. Does that make sense to everybody? 1, the angle is 90. How many understand polar notation? Are you with me? If you do, raise your hands. I want to make sure. This is something you should have been exposed to in math. You may not remember that. That's the magnitude is 1, and it's at an angle of 90. What happens, I'll get rid of that 1 so you can see it. If I take that angle to the numerator, well, 1 is 1, right? It's going to have the same magnitude, but the angle will be negative, e to the minus j 90 degrees. Do you all follow me? Now, I'm going to just write this down one time, and I don't want to have you looking at something that is not really that important. But there's Euler's identity says e to the j any angle is cosine of that angle plus j sine of that angle. How many remember that? There's also the sine form and the cosine form. You should have remembered this, or at least been exposed to it. This is all basic mathematics that you've had. You've had math here, right? If you had math here, you should, I can't say you went to the class, but you should have been exposed to it. This is standard. It's just like with Laplace transforms, S. Everybody should have seen S at least at some point in your life. Guess what? I don't know. Anyway, when I look at that, just take a look at this. If theta is 90 degrees right there, right? And actually what I should do is I have to put plus or minus there because the angle itself, if that's a minus, this becomes minus. So what's the cosine of 90? What's the cosine of 0? 1. What's the cosine of 90?
0.
All right. What's the sine of 90? Minus j. Sine of 90 is 1. It's minus j is minus j, right? That's exactly what this is. This is the same thing as minus j. That's my whole point here. I'm spending a lot of time on. So when I take a look at the impedance of a capacitor, you can put sub C, the impedance or the ratio of voltage to current, you can think of it just as you would resistance, except now it's complex. Got that? That's the only thing you take from this. So this is equal to either 1 over j omega c or minus j over omega c. Now you'll see an x sub c. X just means reactance, don't worry about it. That is the value of the ratio of voltage to current or the complex resistance. Think of it that way. Make sense? How many understand that thought? At least the idea. Now, next, we talk about that's for a capacitor. I'm going to complete this thought before I move on. If you have an inductor, you need to see this applied to appreciate it. But if you have an inductor, and remember an inductor has, this is the symbol, and you have a voltage across that inductor, and you have a current into the positive terminal. Now I'm just trying to isolate the elements so you get this. That's in the time domain. If you were to write the equation that relates voltage to current, you would say what? You would say V, the voltage across that, T, is equal to L di dt. You remember doing that? Now, anytime you see a d dt, the derivative will pull out a j omega. That's the thing you take about. We're going to go to the phasor domain. I want to get right to the point here. So if you think of an inductor and this equation, V now, the phasor form of this, is going to be equal to the derivative with respect to time will bring out a j omega, and L times I phasor. Y'all with me? Now the complex impedance of an inductor is just going to be equal to the ratio of V tilde over I tilde, and that's simply J omega L. And that's it. Now, can y'all follow me on this? I'm going to do this problem, and I'm going to go through it in the frequency domain or phasor domain, and then go into the time domain. You will see that this becomes trivial, but I need your attention. With me? Don't be afraid. You'll be fine. All right, now with this one, I'm even going to use this circuit, but I'm going to try to get a different color marker, and I hope you can see it. I hope. All right. Now remember, this is time domain. When you have V as a function of t, it is in the time domain. The time domain is the observable domain. We can measure that in real time. The phasor domain you can't measure. But the reason we do it, it's useful for analysis. So when we take this and we put it into the frequency domain, we have to first identify the frequency. That's that. Are you with me? Everybody? Now, if you have calculators, now's the time to get them out and learn how to use them here, because there's tons of mistakes with calculators when we talk about complex numbers. And I don't mean a few. I mean like world-class mistakes all the time. Adding two numbers, you get the wrong answer consistently if you don't work with it. Now, you see how this is a value of C by itself, right? The complex impedance of that would be equal to, in other words, the impedance of this, it'll be labeled as X sub C in the book, will be 1 over j omega C or simply minus j over omega c. If you have calculators, I'm going to ask you to give me that value. The minus j I've got down. Minus j is just 1 at an angle of minus 90 degrees. What is 1 over omega c? This is simple math. Omega is 377. C is what? 500 times 10 to the minus 6. Tell me what you get. Anyway. Say again? 5.305. Anybody second that? Anybody else get it? 5.305? Anybody? I try to look for a say. You got it. Thank you. So this is going to be 5.305. The units are ohms. It's the same as resistance. Can you all follow me? Now please watch me. Everybody with me? How many can see that? Far back is what I worry about. Can you guys see it in the back? All right. Now after that, I think I'm going to drop right here just to help everybody visualize what I'm doing. Because there's always some nervousness about this. And I'm going to do it right here because this seems to be the part of the board that's lit up the best. All right, now here's what this circuit translates to. You see this? This is nothing more when we go to the phasor domain. I'm going to have to use this black thing. It just becomes V, and it's the phasor form, will be 12, and it will be at an angle of minus 60 degrees. That's it. You all with me? The units are volts. Everybody follow me on that? So over here, when I'm drawing the circuit, I simply put a voltage here of plus to minus 12 at minus 60 degrees. You could put it 12 e to the minus j 60. The problem with this is the 60 really should be in radians. If you do e to the 60 degrees, e to the j 60, you're going to get some odd numbers. So 60 degrees is pi over 3 radians. Do you all follow me? I prefer leaving it in this form. This is polar form. It's magnitude at angle. You all with me? Now we replace the capacitor with its complex impedance. The gentleman told me that's the value. You all with me? Now I want you to see something. You could put it in this form, or if I look at this, x sub c here, well, the magnitude is 5.305. Does everybody see that, class? So you can put the magnitude there, 5.305, but the angle, minus j is minus 90 degrees. When I think about this, if I have minus j, this is like the j-axis, minus j-axis. Minus j would have a magnitude of 1, but the angle would be minus 90 degrees. Clockwise would be a negative angle, counterclockwise a positive. You all follow me on this, class? I'm going to see this right here. Now I need to make sure you're clear on this. So it doesn't matter what you do, but here, my capacitor, I just replaced that thing with an impedance of, and I'll put down minus j 5.305 ohms. Now that's ohms. This is volts, that's ohms, and I want this. I think they want the current, right? Phasor current, class? And then we'll go to the time domain. Well, first we're going to get the phasor current. Now, how do you always get current if you have a voltage and a resistance? It's not a trick question. Ohm's law, right? V over R, right? Same here. You've got the voltage, you've got the impedance. This phasor current is simply going to be 12 at an angle of minus 60 degrees over, and you can put it either way. I can put this as 5.305 at an angle of minus 90 degrees. Now, do you all follow me? How many see that right here, please? Right? You could put minus j in there. Please get your calculators out. I need to make sure you can calculate this. consistently right and seamlessly, because there are a lot of questions you might have. If you haven't done complex math in a while, this is the time to learn. You're going to be using it a lot from here on out, basically. So what is I phasor? Now you can enter that number however you feel like, and then you could divide by the second number, right? When you get that, the magnitude would be 12 over 5.305 over 5.305. Now the angle, if you look at that, that's minus 60 top, right? If I take the minus 90 to the top, it becomes plus 90. Do you understand the thought on this one? How many do? So I have 90 minus 60, or 30 degrees. So the angle here is 30 degrees. Now can somebody give me 12 over 5.305, the value? That one we can do.
2.262.
Anybody confirm that? 2.262. And the angle is going to be 30 degrees, and that's the phasor current. I'm going to show you how to go to the time domain. And I'm going to tell you, it will become trivial in a second. You all with me? And you can confirm the answer or the solution, I should say. And I'll do it here. So just listen to me and I'll show you how it goes. Now, anytime you're in the phasor domain and you want to go to the time domain, mathematically, in this case it's I, you would say I in the time domain is equal to RE, that is the real part, and now you reintroduce e to the j omega t. We're going to the time domain, so there will be an omega t. Then you multiply it by I phasor. Now, when you do this for the actual problem here, you get the real part of e to the j omega t. The magnitude of I was 2.262, is that right? So it's times 2.262, and the angle here is j, and it's 30 degrees, right? Can you all follow me? Now, how many understand that right there? This is simply going to the time domain. When you take a look at this, and I'm just going to do this one time, you've got two exponential terms. You would add the exponents and get a single e to the j term. So I'm going to get the real part of, and by the way, the 2.262, that's strict real. That can come out in front. You all follow me on this? So this equals my I of t, 2.262, real part of e to the j of omega t plus 30 degrees. Now I'm saying this one more time. That should be 30 times pi over 6, or change to radians. Do you all follow me on this? But we're going to let him slide on this one, because I think his answer is in degrees right there. So when we do this, otherwise omega would have to be in degrees per second, not radians per second. When you do this, here's what happens. Remember when I had e to the j theta is equal to cosine theta plus j sine theta? How many remember that? When we take the real part, it's just the cosine. That's all it is. So here, in the time domain, confirm if this is right, if somebody can. I of t here is just going to be equal to 2.262 times the cosine of omega t, and omega is 377, I could rewrite it, plus 30 degrees, or really plus, and it should be, pi over 6 radians, but I'm going to let them slide. Can anybody confirm that answer? I gave you solutions. Anybody? Do you understand this? Now the trick is this. Just go into the complex domain with the impedance, solve the current in the complex domain, or the voltage, or whatever they want. And if they want the time domain, you're going to have a cosine form, and the angle of that current becomes the angle next to omega t, and the magnitude is just the magnitude. Now, is that the right answer or the solutions? Can anybody confirm? Anybody got access? I put them up there, didn't I? I'm sure I did. If you trust me, it's right. Anybody? Can't see. Anybody look at this problem? I mean, the solutions are there, right?
I think this is 5.6 and going with.
Oh, never mind. Well, that's the right answer. Sorry. I'll put them up. I'm just trying to show you that these are not tough. Now, most of the time, the values of the complex impedance, like if you see an inductor, you won't have to calculate that. It will be given as J 50 ohms, J 100 ohms, just like a resistor. Hang on for 1 second. For a capacitor, it would be minus J, or it would be like 30 at an angle of minus 90 degrees ohms. Go ahead now. What is your question?
I just wanted to know what the number or symbol was after the 2.262.
Cosine.
Oh, sorry.
Sorry. My handwriting is right up there with illegible. Not meant to be, but it seems to be. All right, everybody with me? Okay, now what I want to do is go through problems. If you have your calculators, please get them out. And this is so important because I cannot tell you how many times the error is not in your understanding, it's in the operation of your calculator. And frankly, I use an HP. Does anybody here use an HP? You do? Do you have it with you? Fantastic. I'll use yours. HP is on the way of the dinosaur, basically. Okay. So with all that said, in my opinion, the single best way to understand this is do problems. I can talk to them blue in the face, but that's the way to do it. And so I'm going to go and just kind of knock out some problems. I'm going to go to 510 right away. Here, they're going to give you the value of the impedance of the inductor. And I think you'll see why I'm doing it. If you're wondering how to enter complex numbers and do the calculation, you should have online manuals or YouTube videos that describe it for everything, for PI 84, 83, Inspire, all the other variants. So I'm telling you, this stuff's out there, and you're not the first to use it and won't be the last. All right. So next, this one is, I'm doing 510. The reason I'm choosing this one is I don't want to waste time calculating J omega L. The omega is something you can obviously figure out just by the cosine formula. And L is a simple value. I'm going to go right and show the impedance. So this is 510. Please watch this and get your calculators out. I want to make sure you get consistent answers. So here he has a circuit, and he has a resistance of 2 ohms, and then he has an inductor, and the inductor has an impedance, and he does call this one Z of L equal to J 4 ohms. And what he wants is the input impedance right here seen by this. Zn. Can you all follow me? Now, I'll ask you an obvious question. If this was a regular value of resistor, 4 ohms, how would you do it? Anyway. 2 is in what with 4? Parallel. You could do 2 times 4 over 2 plus 4, right? Or 1 over 1 over 2 plus 1 over 4, right? Either one will get you the right answer. Here, same technique, but we have a complex number. Please try this on your calculators. So when I look at this, if I want Zn, they are in parallel. And I could say my Zn, it depends how you do it. I'm going to do it both ways. I could say this is 2 times J4. Right? This is this times this over the sum. Do you all remember that's one of the ways we can get the parallel combination? How many do? All right, that's one way. Make sure you know how to do these. And this would be over the sum of them. 2 plus J4. Now what I'm going to ask you to do now is give me the magnitude and the angle associated with this. So Zn here would be what? That's J8 over, and here I got 2 plus J4. There's a whole lot of tricks. How many remember you can multiply top and bottom by the conjugate of 2 plus J4 to get a single value? Do you remember this, anybody? No? You can always take the complex conjugate of the bottom, multiply top and bottom by that. Or what I recommend you do is this. You can say, if it's just magnitude that you want, it would be divided by 2 squared plus 4 squared. Remember that J is a 90-degree bend, right? That's the magnitude. Think of a triangle, correct? And what's the angle going to be down here? Well, it would be the inverse tangent of the opposite, or 4, over the adjacent, or 2. Can you all follow me? You don't know? Did you understand? Do you have a question?
No, he asked me a question.
I was just curious what the numbers are next to the ZN.
What this is?
Yes, sir.
That's J4. Let me try to be neater. It's the problem that, so this is simply J4 ohms. Can y'all see this? If you have access to your books, you can look. All right, now, that's the angle here. I'm just going to show you, if you can actually do this, your calculators do this. If you simply plug in 2 times J4 on top and 2 plus J4 on the bottom, your calculators can render that in terms of a magnitude and an angle. I don't know how. Oh, you got an HP. Anybody have a TI that knows how to do it? How many have a TI Inspire? Most of you have that? No? What TI do you have?
84.
How many have the 84? When somebody figures it out, raise your hand. It's not hard. It's trivial, actually. So here for Zn, I'll just tell you what you can get. This is 8 on top magnitude, that's 90 degrees. You agree with that? So you can say this is 8 at 90 degrees. Downstairs, you got a magnitude of 2 squared plus 4 squared square root. That's 16 plus 4 square root of 20, right? So the magnitude square root of 20. Now, what's an inverse tan of 2? 4 over 2 is 2, right? What's the inverse tan of that, degrees? I don't know that. Say again?
63.44.
63.44. Anybody confirm? All right, so this is really an angle of 63.44 degrees. Now, you can say the magnitude would be 8 over square root of 20. And then on top, your angle is 90, be an angle of 90 minus 63.44. You're gonna have to help me with this one. So I got 8 over square root of 2, or square root of 20, what is that? Anyone? About 2 something?
Like 1.78.
1.78. What's the angle? 90 minus 63 is 26.66, is that right? Just take 90 minus 63. Is that right? Class? Anybody confirm that? How many got that? Something like that. All right. Can you take that and go from polar on your calculator to real and complex? I want to give both values, all right? So you should have a polar to rectangular set of, I guess, button instructions where you hit like function, pole to rec or something like this. I don't know actually on your calculator. And tell me what you get. Anyone? Anyone? I'm really trying to help you. You have no idea how you go crazy if you don't do this stuff now.
1.59 plus 0.8 J.
1.59 plus J, say that again?
0.8.
0.8. Anybody confirm that? Anybody? Please know how to do this. All right, did you get that? Anybody?
I got 1.6.
All right, well, we got 596, it's about the same, right? Call it 1.59, 1.6. Is the second part plus J.8 the same? If you ever wonder about square this term, take the square root, it better be 1.78 about. Follow me? How many understand that? All right? Now that's what the impedance of this complex impedance could be. You could do it this way as well. Please listen. If they are in parallel, you could say Zn, and it doesn't matter the way, is 1 over the impedance of the first one is 1/2, right? Plus 1 over the impedance of the second one is 1 over J4. Now, can you all follow me on that? A lot of people at this point, they don't know exactly what to do, but your calculator does. This is 0.5. This is 0.25. If J is at the bottom, J is 1 at an angle of 90. Upstairs, it's 1 at an angle of -90. Do you all follow me on this? So really I can say that this is 1 over 0.5. 1 over 4 is equal to 0.25. I have a 1 over J. When it comes up here, it becomes -J. That would be the same thing. Would somebody tell me, if you get that and go from rectangular to polar, remember that's in the denominator, tell me if you get 1.78. Please know how to do this. I am saving your lives here. Believe me, this course is taught a lot of times, they don't spend this time, and the first time they have to use this, a whole lot of people get like zeros and stuff. I'm really trying to help you. Did you get it?
I think so.
That's the stuff that, when you hear flight, an air traffic controller say, I think you're okay. Or a surgeon, I think you got it. You think? Just try that, see if you get the same value. Anybody confirm that, please? Let me know. All right, thank God. Yeah?
How do you convert from one of the real numbers plus high? How do you
All right, what calculator do you have?
TIA.
84. Anybody have an 84 know how to do it? Anybody, could you help him, sir? Just go over there now.
No, you're good. You don't have to.
Well, I'm telling you right now, I'm trying to do this in class because I don't know. And when you send me emails, you're wasting your time. I don't know your calculator. If you got my calculator, I should have. But your friends here are the best thing. And if you have that group me page, right? If you got a group me thing, please show them how. Any help you can give other people will be a tremendous benefit. You're doing a good thing for your fellow man or woman. All right, are we clear on this, class? Now, next one. First, try it. Do you get it? All right, next one we're going to do a little more involved. This is going to be 512. If you have, I don't mind you chatting. If you want to show somebody how to use the calculator, if you know how to do it, please talk to your friends and don't blow this off. Because this next quiz, if you don't know this, you're gonna, not on Thursday night, you're not gonna figure it out probably. There's a lot of stuff coming down the pipe back here.
I found the function. Right there.
All right. So now I'm going to do 512. Little more complexity, same idea. Please make sure you see this. So 512. Here you got 4 and J2. They have this. A and B. And they say it's 4 plus J2. That's ohms. And then over here, they have 2. That was supposed to be an inductor, but he didn't show it. So he has 2 ohms. And then he has an inductor, it looks like a resistor on mine, J4. An inductor will have a positive J sensitive. And this is minus J2. Now I'm going to show you something that will help you tremendously. Everybody understand the problem? Okay. Let me have your attention here. This is important. When you look at this, and this isn't drawn exactly the best way, but what I should do is this so you can see it better. They want this impedance, input impedance. Can you all follow me? Now, what I want you to do is ask yourself first, what would the likely simplification be if they were just resistors? Can everybody see these two are in series? If you can, let me see that. In the far back, can you guys see that? Far back. Now what else? How about right here? Are they all in series, class? Yes? How many see that? It's important, trust me. Well, if they're in series, normally you just add up the values and replace that with a single resistor, isn't that right? Here, we can do that, but we're going to label them in terms of a complex resistance. Now, listen to me. You see how that's a plus J4. Can everybody see that? And that is a minus J2. When you add them up, you get J2. How many see that? So what I can do is take this, and I can say, well, that circuit really looks like this. It looks like I have 4 here and J2 ohms. And then I have 2, and I have J2. Everybody follow me on this. I'm just trying to help you see the simplification and the reason. Now at that point, you have 2 resistors in parallel. If you were 2 complex resistances in parallel, you can take this impedance, complex resistance, and multiply it by that one, and then divide by the sum. That's one method. You all follow me? Or you can say 1 over this impedance plus 1 over that impedance. Either one will give you the correct answer. I guess the reason you choose one over the other is because one is more familiar to you or easier. So get your calculators out and try them. Did you have a question?
So why were we able to turn that into just 2 without J there?
First, you agree they're all in series?
Yes.
Now we can add them up, right? We have 2
Oh, I see the 2 now.
plus
I see the 2.
J4 minus J2. That's the reason. Good question. Can everybody follow me? So I want you to make sure you can do this. If you're trying to calculate the value between here and here, you can take that impedance times that impedance over the sum. I'll do that. Or you can take 1 over that impedance plus 1 over that impedance. Do you all follow? Either one will give you the same answer. Get your calculus and try this one. So for this one, if I do it by multiplying them, I can say this value, that Zn right there, would be equal to 4 plus J2. Your calculators will do this easy, times 2 plus J2. And then divide it by the sum. So you would add the real parts, which would be 6, and then you add the imaginary, which would be plus J4. I want you to just make sure you see what I've done and understand it. Do you see that? You're going to find out in time, you will be able to enter this value in a memory. And then you can put this value in a memory. And literally, you can recall one, multiply, recall the other, equal, divide by, recall one plus recall two. And it becomes very, very efficient to do. But you've got to get familiar with your calculators. And your calculators will probably be the biggest headache, not the theory at this point. So I'm just trying to help you. What do you get for this? Well, if you're playing around with your calculators, that's fine. But downstairs I got 6 plus J4. Upstairs I have 4 times 2 is 8, right? And then I have what? I have J2 times J2. J times J is -1, so I have -4. So I took these two first, then these two, because J times J would be -1. How many agree with that? Got to make sure, at least I know you understand the basic math. Then you have these intermediate, you have a complex or a J times a real, that's J4, and this would be J8, so this would be plus J12. Now I'm just doing this to show you. Your calculators will be able to get this answer in a blink of an eye. When I do this, you can see I have 4 minus 8. Let me put it over here. So I have Zn here. Well, 8 minus 4 is going to be 4. Then I have plus J12. Your calculators will do this much faster. They don't need all these steps. Downstairs it's 6 plus J4. Can you all follow me? I'm just going through the math. Now you can take magnitude of the bottom at an angle, magnitude at the top of the angle, and then divide them. But at that point, it doesn't matter how you get the answer. They always will give you the same answer if you know how to use your calculator. Can anybody give me that answer with your calculator? Get used to doing these quickly. Well, the magnitude on the top would be what? 4 squared is 16, right? Then I got what? 12 squared is 144. So square root of 16 plus 144. Downstairs it's 36 plus 16, right? Square root. So you can get the magnitude fairly straightforward, right? The angle, here it's an inverse tan of 4 over 6. On the top it's inverse tan of 12 over 4 or 3. Can you all see this? So what do you get for this, anybody? Magnitude? Or give me real and imaginary, how's that?
1.385.
Hold on. Go ahead.
Plus 1.07.
Plus J?
Or, yeah, plus J.
1 point, say it again.
1.07.
Okay. Ohms.
Yes.
All right. Y'all hear that? Anybody else get that? Okay, good. You're catching on. Are those TI-84? Which calculator? 84 back then? Anybody have an 83
I literally just.
that they're using to get the correct? Anybody have an Inspire? How about an 89? Any other calculators where you got the right answer? Not you. You got an HP, you don't count. All right, now class, it's about over, and I see that the last, just take your quizzes. Could you make sure the remainder of the quizzes come up front? Check your quizzes. Now, I'm going to give you a bunch of problems to do. Yes, sir? Hold on.
So, is there like a specific mode we're supposed to be?
Any what?
Is there a mode we're supposed to be? Yes.
Oh, God.
There's like 2 different ones where we are each of the data.
Can anybody help him? He's asking for the mode in which calculator? Which calculator? 84. That guy can help you.
Dude, I know you.
Please learn how to use your calculator.